Hello class, welcome to Algebra Lesson 3.3, which is all about transforming linear functions. By the end of this lesson, you should be able to transform linear functions. Alright, let's start with example 1, vertical translations of linear functions. The positions of two baby sea turtles making their way to the water after hatching from their eggs is recorded. They move at the same speed, with Byron starting 2 feet ahead of Frank's starting point. Okay, so we have a nice little graph there, and the book was nice enough to put a coordinate plane on it even. Alright, what function represents each turtle's position as they make their way toward the shore? Let's start with Frank here. Okay, so Frank starts basically on our graph at the origin, right? And when we are looking at these graphs, we're going to write equations that are like what we practiced back in chapter 2, and then we're going to turn those equations into function using that function notation that we've been practicing this chapter. So let's start with Frank. We have y equals, what's the slope of his line? It goes up 1 and then right 1, so that's a positive 1 over a positive 1. So a slope of 1x plus, where does it cross the y-axis? 0. So I could write y equals x plus 0, or I could just say y equals x. And turning that into function notation, I would say f of x equals x. And so that is Frank's function. Now let's look at Byron's. So we have Byron, and he's moving at the same speed as Frank, so up 1 over 1. So his slope is a positive 1 as well, so y equals 1x plus, but he starts 2 feet closer to the sea already. So I'm going to put y equals x plus 2 as his equation. Change that to function notation. F of x equals x plus 2. And that is Byron's function. Okay, so that's the first part of this problem, was just writing a function to represent each turtle's position as they make their way toward the shore. Now, if we take away kind of the image from that graph and look at those two different lines, okay, so the blue line was Frank, and then the red line was Byron. Okay, so just to help you remember, what happens to the graph of a function when you add a constant to its output? You might have listened to me read that, or might have read that yourself and had a momentary panic because you see a couple of words like constant that you're like, that rings a bell, or maybe that doesn't ring a bell, and you are just lost right then and there. That's okay. I'll remind you what a constant is in a minute. Another word you might be confused about is output. This is something that we talked about when we began working with functions this chapter. Okay, so remember, output is basically just another way of saying y. Remember, input is x, output is y. Now, constant is any number without a variable. So let's remember, our function for Byron, we said, was, they used g of x for Byron. So g of x equals x plus 2, right? Because he started 2 feet closer. And then Frank's was f of x equals x. So that constant that is talked about is that plus 2. Okay, we added a whole number after our variable. That is considered a constant. And when we added that plus 2, notice it moved the whole line up 2 units. So whenever you have x plus or minus a number, that constant, is going to be what shifts your graph up or down. Okay, so even without having the picture of the graph, if we just had this information right here, I would still know that the graph was shifted up 2 units because it has the plus 2. Okay? Now, this question is for you to try on your own. Let f of x equals negative 4x. Okay, so that's what we started with. So in this case, imagine this is like Frank's line. Okay? And then we're going to compare how does the graph of g of x equals negative 4x minus 3 compare to the graph of f. So imagine this is Frank's line and this is Byron's. And how did that change? hopefully you said that it goes down 3 units, because it wasn't a positive 3, it was a negative 3. So it goes down 3 units. And that is all that you have to say for that problem, okay? Now, let's talk about what a transformation is. So transformation, you learned back in pre-algebra and even in earlier years that a transformation is any time you move something, okay? So whether that means that you translate it, that's when you like slide it left, right, up, down, or maybe you rotate it or you reflect it. We're only going to focus on translations right now. Really, and then later on we'll talk about like how you can stretch and compress something. But a translation, remember, is just sliding something around. And a transformation is like the overarching name for that. So if we look at this first graph on the left, this is a picture of a vertical translation. It moved from blue to red, it went up. And then if you compare the graph of G, you can see it from blue to red, it goes left. Okay? So how does adding a constant, usually when we talk about constants, we use the variable k. So that's something good for you to note. Whenever you see k, we're typically talking about a constant. How does adding a constant k to the input, remember input is x, of a linear function affect its graph? Okay, so we're going to consider two graphs. F of x equals 2x minus 4, and then g of x equals 2 times the quantity of x plus 5 minus 4. So notice that f of x and g of x look close to the same, but instead of writing just x, g of x switched to x plus 5. So let's talk about how things kind of change when we have a situation like that, whenever you're adding or subtracting something from the x value. So first, let's start by making a table of values for those two graphs. So the book made it where we had a column for x, then we had a column for f of x, and then they made a separate column for x plus 5, just so that way it was easier to plug into the g of x. So like if we plug in negative 4 in, 2 times negative 4 is negative 8. Negative 8 minus 4 is negative 12. And then if we plug negative 4 into x plus 5, we get a positive 1. So I'm going to take that positive 1 and plug it into my g of x function. I'd say 2 times 1 minus 4, that's a negative 2. And then I can shift down, look at negative 3, negative 2, and so on and so forth, okay? So I'm going to reveal that graph to you so you can see how the numbers changed. So it started when I had that negative 4. It started at a negative 12 for f of x, and for g of x, it made it a much bigger number, right? Negative 2. And then for negative 3, it was a negative 10. It made it a bigger number, 0. Negative 8 became a positive 2. Negative 4 became a positive 6. Negative 2 became a positive 8. Okay? And so on and so forth through that line. So let's look at what that graph ends up looking like when you graph those points. So if we graph those, we have f of x is that blue line, and you can see that everything just got shifted to the left, okay? Everything got shifted to the left. And some of you might be asking, but Miss Johnson, why can't we just say, like, start at this point and say that, oh, look, it went up X number of units? So the reason we can't do that, the reason we won't do that, is because whenever the number is in with the X, like that, we're going to be talking about left and right translations, okay? Left and right translations. So then adding a constant k to the input of the function translates the graph horizontally by k units. So it could move it left, it could move it right. But I do want to point out the fact that we had x plus 5, and look what direction it went. X plus 5 went to the left. So when you're doing horizontal translations, if you have x plus a number, that is going to move left. And if you have x minus a number, that is going to move to the right. Okay, just to help you keep track of what direction things are moving. Okay, question number 2. Let f of x equal 3x plus 7. How does the graph of g of x equals 3 times the quantity of x minus 4 plus 7 compare to the graph of f? Good luck. All right, for this problem, hopefully you said, I have a number, a constant in with my x, and I have x minus, and Miss Johnson just told me that minus means that we move to the right. So hopefully you said, this graph is going to move right 4 units. Example 3. How does multiplying the outputs, remember outputs the y, of a linear function affect its graph? Okay, so we have f of x equals just x plus 1, and g of x equals 4 times all of f of x. Okay, so 4 times everything that f of x was. So I have my graph here, or sorry, not graph, my table here on the left, and then my graph here on the right. So by plugging in -3 to f of x, I got -2. Plugging -3 into g of x, I ended up at -8. -2 became a -1 and a -4. -1 became a 0 and a 0. Okay, so they have that point in common. And then putting a 0 in, I got a 1 and then a 4. So if you look at these numbers and compare, do you see how the y, or the g of x, I should say, the g of x numbers are all a lot bigger? That's because multiplying by 4 does what we call a vertical stretch. Okay, a vertical stretch is anytime your constant, so k, is greater than 1. Anytime you'll get a vertical stretch anytime k is greater than 1. And actually it's the absolute value of k. So even if you had like a -4, you do the absolute value and you'd say, is that bigger than 1? Yes, it's a vertical stretch. But we'll talk about negatives more later. Now, a vertical stretch means that it's going to kind of, imagine you have like a ball of putty in your hands and you pull your left hand up and your right hand down while holding that putty. That stretches it, right? That makes it thinner. That makes it go farther. And then we have something called a vertical compression. And that is when you move that left hand back down, that right hand back up. It's when you're kind of squishing that putty back together. And that happens anytime your k value is a fraction that's less than 1. Okay, so anytime it's a decimal that's less than 1 and greater than 0, so the absolute value, again, because we're just going to focus on the positive value of k. Anytime it meets that criteria, it's what's called a vertical compression. All right, then what about a slightly different case? What if we multiply the input, or the x value, instead? So this time we took x plus 1, but then we put a 3 with just the x, okay? Just the x. So you can see that my input and output, they choose kind of 2 different things to show you how it shifts. between these two lines. And so horizontal stretches and horizontal compressions function the same way as vertical compressions in the fact that if you have something between 0 and 1, it is it's kind of the opposite. So here it's a horizontal stretch when it meets that criteria. So horizontal stretch and vertical compressions have the same criteria of the constant is between 0 and 1. And then horizontal compressions and vertical stretches have the same criteria of the absolute value of k is greater than 1. Okay? And so a horizontal stretch is when it gets kind of like pulled left and right. And then a horizontal compression is when it gets pushed back in. So you can see if you look at this graph of f, that line is getting pushed back in towards the middle. So this is considered a horizontal compression. And we can confirm that because our k value is 3, which is greater than 1. And I know that thinking about graphs this way can take a lot of time to get used to. Even I still pause and think about if I'm saying the right words, okay? So if you're feeling overwhelmed by this, that's totally normal. It's okay. What's not okay is if you just sit there confused and don't ask questions, okay? So if you're feeling confused, that's fine. But make sure you do something about that and you ask questions, you ask for help, you look at other resources, you make sure that you actually understand this material. All right, knowing the information I just gave you, let's let f of x equal x minus 2. How does the graph of g of x equals 0.25 times the quantity of x minus 2 compare to the graph of f? So I want you to think, okay, is this going to be a horizontal or vertical? And is it going to be a compression or a stretch? That's what I'm looking for here. Good luck. Hopefully you noticed that the number was outside of the parentheses. It wasn't just with the x, so that means that it's going to be a vertical something. And since it's between 0 and 1, it's a vertical compression. Okay? Let's try one more. Go ahead and solve this one on your own. Let f of x equals x minus 2 and g of x equals 0.5x minus 2. How do those compare to each other? Good luck. Okay, hopefully you noticed that our 0.5 was just with the x this time. So that means that it's going to be a horizontal transformation. And since it's between 0 and 1, it's a horizontal stretch. And in this case, by a factor of 0.5. Sometimes the book will ask you, what is the factor that it changes by? And that's just the number that is being multiplied in. So in this case, it's 0.5. On the last problem, it was 0.25, okay? Here is a lovely little summary that you can take a picture of and have as part of your notes to reference back. I think this is a great thing for you to take a screenshot of, but that's up to you. If that helps you, great. If it doesn't, that's fine. You need to find some way to get this information to stay in your brain, though. So whether that means you make some flashcards or you just keep rereading this, you write it down yourself, whatever you need to do, make sure you do it, okay? I hope you have a fantastic day.